Hey, man, here. Today, the lesson is about moles and molar mass calculations. Now, it's not this lovely creature here. It's a slightly different kind of mole that we use in chemistry. The big question at the end is you should be able to answer if I ask, how much does a mole weigh? That would be like asking, how much does a dozen weigh? So if I say, how much does a dozen weigh? Well, a dozen what? Eggs, donuts, cars, what am I talking about? So the substance makes a big difference. So just like with the dozen, it's a word that means a number. So dozen means 12. So I could have a dozen of, like I said, a bunch of different things. 2 dozen is 2 of them. Of means multiply in math terms. So 2 of the 12. So 2 times 12 is 24. If I had a half dozen, half of a dozen, so half times 1 dozen, and that would equal, not 24, that would equal 6. So just like that, mole is a number that means, or mole is a word that represents this number. That is a horrible, horrible number. So instead of talking about the number, we say a mole. Dozen's easy because we have the number 12. We can do some math with the number 12. It's harder to do math with this. But a mole equals 6.022 to the 10 to the 23rd of something. So like I could have a dozen donuts, I could have a mole of donuts. And you would never have to eat anything else for the rest of your life, which would kind of be horrible. Just like if I have 2 dozen donuts, I have 2 times a dozen. If I have 2 moles, I have 2 times that giant number. Now, if you don't like having to worry about the exponent thing on here, the 10 to the, you can do the math without that. So what if a mole equaled 6? So if I have 2 moles, I have 2 sixes, so I have 12. So think of it like that. A mole equals 6, and then you get the number 12 times 10 to the 23rd. So 12 times 10 to the 23rd is the same as 1.2 times 10 to the 24th. That's just the correct scientific notation. If I have half a mole, so half a dozen, it's half times a dozen, so half times 12 is 6. Half a mole is half times 6, so, half of 6 is 3. Alright, so it's 3 times 10 to the 23rd. So do the math with this, first off, then just add on the 23rd. But yeah, it's too unimaginable of a number to really work with very easily, and it's tough to say. So instead of saying 6.22 times 10 to the 23rd over and over and over, you can say Avogadro's number. This fabulous looking guy is Avogadro. He didn't think of this number, but it's named in honor of him. What he figured out was, if I have, let's say, 10 molecules of oxygen and 10 molecules of hydrogen and 10 molecules of iodine, if I had a balloon, or 3 balloons with these different things, if you looked at hydrogen and iodine in particular, iodine weighs like over 100 times as much as hydrogen. So the balloon would weigh 100 times as much. But if they're all the same temperature and all like in the same room, so the air pressure is the same, all 3 of those balloons would be the same volume. That's what Avogadro worked with. 10 molecules of each one of these would all have the same volume. 100 molecules would all have the same volumes. And so they worked out what is the actual number that we should base this stuff on. That was a mole. So Avogadro's number, instead of saying the whole 6.22 thing. So the whole Avogadro's number came about by working and figuring out the molar mass. The molar mass is the mass of 1 mole of a compound or element. So I could have the dozen mass. What's the dozen mass of a dozen donuts? Well, it's, whatever they weigh. So let's say 1 pound per dozen. What's the dozen mass of some eggs? It's 2 pounds per dozen. It's whatever it is per dozen, or in this case, it's per mole. So, according to the periodic table, if we back up a little bit, we know that one atom of carbon has a mass of 12 AMU. So if we look at the periodic table, carbon, there you go, 12.011 AMUs. That's 12 protons plus neutrons in the average atom. But AMUs are not very helpful. We don't deal with one atom at a time, we deal with a whole lot. So instead of one atom, that number of 602 times 10 to the 23rd, Avogadro's number, came because they figured out how many atoms does it take to turn that unit of AMU into a nicer unit of grams. Because I would much rather work with grams because it's familiar than trying to figure out things about one atom. So this is how many atoms it takes to just change the unit. So now as I look at carbon, the molar mass is 12.01 grams per mole. The atomic mass is 12.011 AMUs per atom. So we can just look at this. What's the molar mass of molybdenum? 96. What's the molar mass of strontium? 87.62. So molar mass is just what those things would equal. It's pretty simple. Also though, what if I have, let's see, for hydrogen, so what if I have 3 grams of hydrogen? What would that mean? Well, if 1 gram is 1 mole, that must mean 3 grams equals 3 moles. Which is kind of cool. So we can figure out, if you weigh something, you can figure out how many atoms are inside it, give or take a few 100,000 or million. So you guys have this sheet to help you out when you do this math. The whole point of us figuring out moles is not so we can figure out moles. It doesn't matter if I know how many moles are in something, but let's say I have this big fish tank. I know how much water it can hold, and I want to put some jellyfish in there, so I need some salt water. So I have some instructions. They tell me the concentration of salt that I need. So if I have this concentration, I know I need this much water, the volume. How do I know how much salt to put in? What's the mass of salt that I have to weigh out and pour into that? Because that's how I measure salt, as I weigh it. So I can use some math and figure out moles. Why do I care about moles? I don't. But moles are the key to getting anywhere else. So I can go around there and then figure out, oh, I need 20 pounds of salt. Or I've got some helium in a tank. I know how much helium I have in my tank. It's however many kilograms. I want to know how big of a balloon can I blow up. So if I figure out the moles, I can figure out the size of the balloon, the liters. And this is what Avogadro worked on, was every mole of gas on certain conditions will have that much volume. So really, moles are just the key to figuring out all of these other types of measurements, which is, again, kind of cool that you can figure out from one thing to another. So we looked at molar mass of individual things. So carbon was 12.011. Oxygen would be, look on the table, 16 grams per mole. Molar mass of a compound, like water, is equal to the mass of each element that produced it. So water is produced by adding 2 H's and an O. So if you look on the periodic table, it will tell you it's about 1 plus 1 plus 16, or 2 H's and an O. That adds up to 18 grams per mole, and we write that as grams per mole. Notice the abbreviation for mole is MOL, because the E is the really time-consuming letter to write, and so they just save you that trouble. So 18 grams per mole. That's different from saying 18 grams when you do the math, because 18 grams is like, oh, I have 18 grams sitting here. Water is, no matter how much I have sitting here, is always 18 grams for every mole. That's what the per is for every. Alright, so pause this, see if you can do NaCl, then unpause it, and see if you're right. So NaCl is made out of Na plus Cl. You look on the periodic table, It's 23 plus about 35. You could say 35 and a half. It's kind of where you want to round some of these things to. So that would be altogether 58 or 58 and a half grams per mole for salt. So what if I had like 120 grams of it? What would that mean? So if every mole is 58 grams, if I have 120 times, or divided by the 58 grams per mole, that would be 2 moles, just a little bit over, 2.06 moles. What if I had 1.5 moles of salt? Of means multiply. So 1.5 moles times 58 grams per mole would be 87 grams. So just some examples of the kind of math we can do, which is shown on this. So I went from moles to grams. I went from 1.5 up to mass, and I went from the mass of what did I say, 200 or something. I went from the mass to the moles. So you can go either way on that using just this nice little map that's set up for you. Just plug the numbers in, find the molar mass on the periodic table. We get a little tricky, so we can pause this, then play it. Calcium hydroxide. It's made out of calcium and 2 OHs. The 2 applies to everything inside there. Calcium and 2 O's and 2 H's, which altogether equals 74. So both O's weigh 16, both H's weigh 1. So 74 grams per mole is the molar mass of calcium hydroxide. Beryllium nitrate. Again, pause, play. For this, the 2 applies to the N and to the O. So I have 2 NO3s. So that's 2 N's and 6, 3 plus 3, 6 oxygens. So altogether that gets me 133 grams per mole. So you have a better idea of what a mole kind of means as you look at it. A mole of oxygen would weigh twice what individual oxygens would weigh, so that's about 32 grams per mole. A mole of oxygen would be 22 liters of gas, so that's 11 2-liter bottles. A mole of aluminum is about 2 cans. Every can is about 13 grams. A mole of water would be 18 milliliters. A mole of salt would be about 1/4 of a cup. A mole of sugar, that's a really big one. You have C6H22O11. That's a whole lot of things you're adding together. That's 342 grams per mole. That's pretty heavy. That's 3/4 of a pound. So mole's just that number of atoms. If you add those all up, you can figure out in general what different common things would weigh. You haven't been able to see me since I had that calculator up. So, to review, work with moles like you would work with a dozen. If you're confused, think, okay, what would I do with a dozen? If I have 2 dozen, okay. If I have half a dozen, the weight of half a dozen is half of the weight of a dozen. Molar mass is the mass of 1 mole of that substance. So you can add up the mass of each element. So, oh, I've got 3 oxygens. All right, oxygen plus oxygen plus oxygen, that's 3/16. You can work from moles to mass or mass to moles. So going one way, you're going to multiply by the molar mass. Going the other way, you're going to divide by molar mass. But the key is, anytime you're working back and forth between these, is on both of these, you have to know the molar mass. Now, what we're going to look at next time is molarities. We'll be working in this corner as a whole. Molarity is concentration. So the homework is, in addition to these notes, go make some Kool-Aid or some juice where you have the can that you have to mix with water. That's the homework. So make some Kool-Aid or some juice. Or maybe some Jell-O. That might work too. All right. So good luck with that. Tell me how it turns out. But it's tasty.